Yeah, so we're going to get started on our critical minerals session, and we're going to kick it off with Jerome Downey, PhD. He's the department head of metallurgical and materials engineering at Montana Tech. Jerry's the Goldcorp professor of extractive metallurgy at Montana Tech, where he serves as the department head. His 40 years of professional experience includes industrial operations, applied process research and development, and corporate management. His expertise includes chemical and metallurgical thermodynamics, thermal processing, material synthesis and processing, and hazmat treatment. And currently he's researching the study of fundamental properties of slags, molten salts, and glasses, extraction and refining of rare earth elements, synthesis and sintering of non-oxide ceramic and composite materials, and applications of nanocomposite particles for water remediation. He's going to be presenting with Tegan Leitzke. She is a postdoctoral researcher. She's also a PhD, and her research is in the metallurgical and materials engineering department at Montana Tech. She earned her BS in physics at St. Norbert College, master's in material science and engineering at Montana Tech, and her PhD in material science at Montana Tech. Her technical experience includes aqueous processing, magnetic separation, environmental remediation, and water treatment. And currently she's researching rare earth element separations, critical mineral recovery from slag waste and wastewater, and applications of magnetically susceptible adsorbents for water remediation. They're going to give us a presentation on waste to treasure, novel processes for recovering high-value materials from unconventional sources. So please welcome them.
Thank you, Steve. So yeah, as Steve said, my name is Tegan. Our talk today will highlight some of the cutting-edge research the Downey Research Group is working on with the focus of utilization of waste products and recovery of high-value materials, including critical minerals and rare earth elements from these wastes. And a quick preface to our presentation, the technologies today are in the patent process, therefore we can only provide limited details about what we're doing. And I will start by giving a little bit of background on these waste products and critical minerals and rare earth elements, and then we'll move into our two processes. So, some unconventional sources for waste products. Many waste products are simply disposed of without consideration of valuable materials they may contain or produce. The waste products we are focused on include scrap, such as in cars, computers, and printed circuit boards, end-of-service life materials such as magnets, motors, and batteries, and then metallurgical byproducts and plastic materials. So millions of tons of waste products are produced annually and can be toxic to the environment, humans, and ecosystems. Also, storage of these wastes can be difficult with limited space availability, and they also can have the potential for leaching toxins. By recycling materials, we can kind of shift a little bit of focus from needing to mine for these resources to using readily available waste products. And also by recycling, we can reduce environmental impacts caused by generation and storage of these waste products. Proposed strategies for waste utilization have not been widely adopted because they are not economic and or do not have sufficient political or economic or environmental incentive to implement. Many of the technologies are also energy intensive and have high carbon emissions. Our ultimate goal is the transformation of legacy wastes into value-added products, especially concerning the critical minerals and rare earth elements. So with the shift to clean energy technologies such as solar plants, wind farms, electric vehicles, and drones, the demand for materials, especially these critical minerals and REEs, will drastically increase, possibly triple by 2035 for rare earth elements. And additionally, nearly all CMs and REEs are imported, therefore development of technologies to help recycle and recover these materials is of great importance to material security for the U.S. So many times the critical minerals and REEs are in low concentrations. We're looking at like parts per billion. Therefore, they're not really economical to recover using conventional technologies. And these technologies a lot of times have long processing times, are costly and inefficient. A lot of times they will be, you'll have to do like 100 steps to get like a purified product, especially for REEs. And conventional technologies also look at specific types of feedstocks, since they can drastically change in chemical and physical characteristics depending on where they were sourced from and how they were processed. So the Energy Act of 2020 defines a critical mineral as a non-fuel mineral or a material essential to the economic or national security of the U.S., and which has a supply chain vulnerable to disruption. Recovery of these materials from geogenic and anthropogenic sources is crucial to being able to sustain the production of items that use CMs, such as antimony in lead-acid batteries, lithium and manganese, which are used in chargeable and rechargeable batteries. Scandium is used in solid oxide fuel cells. We also have arsenic, gallium, and rubidium are used in semiconductors and electronics. Bismuth is used a lot in the medical and atomic research fields. And then we have zinc in galvanized steel. So for the rare earths have gotten a lot of traction recently and are used in a lot of current technologies with applications in catalytic converters with cerium, lasers with terbium and ytterbium, neodymium and dysprosium magnets are very common and useful. We've got lanthanum-based ceramics. In airplane engines, we've got praseodymium, and then gallium is used as an MRI contrast. So there's a lot of useful applications for REEs and CMs, which is why we're all concerned about them nowadays and would like to make sure we have a constant supply of those. So one of the processes that we'll be talking about today, this was sponsored by the DOE EPSCoR, and we're looking at recovery of metals from metallurgical slags. So we'll take a brief look at slags. So slags are byproducts of smelting iron, copper, lead, nickel, and other metal-containing ores and concentrates and recycled metals. And while not classified as hazardous by the EPA, it is possible that some hazardous materials and metals could leach out of these slags. And then we'll get to this slide a little bit later, but slags can also contain many critical and useful metals, and I'll go over a few of those. And as we'll see on the next slide, slags can have a large variety of compositions depending on what process they came from and what was being smelted. So further current recycling methods incur a loss of metals value, which is a waste of natural resources and decreases sustainability of the recycling process. Also, if the contained metals are not removed from the slags prior to recycling of slag that is currently done, the grinding energy is greatly increased and the slag hardness is much higher. So two of the most common waste slags are copper and steel slags. Copper slag is a phthalate slag and EAF slag is a calcium silicate slag, and these slags act as repositories for impurities, and some of the impurities contain toxic or hazardous materials, which is why they can be an environmental concern. We can clearly see a wide range of components that make up these slags due to the varying feedstocks, initial feedstocks, and processing operations. So what are some high-value materials in waste slags? So for copper slags, there's obviously copper, and we use that in electrical equipment and construction. We've got zinc used in galvanized steel. Cobalt is used in rechargeable batteries and superalloys, iron in steelmaking applications, and then molybdenum in thermocouples and cathodes. Also in the EAF slags, we have some iron and moly again, along with chromium, which is used in alloys such as Inconel, vanadium, which is used in surgical tools, manganese, which is used in steelmaking, and could be used for railways, And then nickel, which again is another stainless steel alloy additive and is used in different applications such as the Chrysler building. So in addition to slags, this process also looks at waste plastics. So we've got the four probably most common waste plastics are HDPE, LDPE, PET, and PP. And in the last 10 years, more plastic has been produced than in the previous century, where we have 8 to 10 million metric tons entering the ocean each year, and 80% of the marine pollution is this plastic waste. And of that 80%, 49% of that pollution are single-use plastics, so like straws and bags and that sort of thing. And out of all this plastic that is ending up specifically in the ocean that I'm talking about here, but only about 10% of plastics are actually being recycled. So, what are we going to do with the plastic? Well, we're going to pyrolyze it. So we're looking at cold plasma or non-thermal plasma, which has extremely fast kinetics and optimum heat generation with a high degree of energy efficiency. Non-thermal plasmas range from room temperature to over 2500 C compared to thermal plasmas, which are about 6,000 to 8,000 C. And plastics pyrolyze at only 600 to 900 C, so we don't really need to use the thermal plasmas for this process. And the plastic pyrolysis can generate 3 products. So we can get pyrolysis oil, which is an intermediary step to produce fuels, but it does add an additional cost because it has to go through a distillation process to obtain the oil. We can get carbon black, which is used as a reinforcement in tire and rubber products, as well as an additive in plastics, paints, and inks. And what we're really looking at is this syngas for our application. So syngas is used in smelt reduction technologies to produce molten iron and direct reduction of iron from iron ore processing. And the one nice thing about using pyrolysis to do this is that we don't have to use coal or natural gas to generate this syngas. So here's our overall process. So it's a gas-based reduction. Slag is heated to an elevated temperature under an inert atmosphere. And then we're going to add, once we hit our target temperature, we'll add in our reducing gases. And then we're going to cool it down along with the gases and the inert gas to make sure we don't reoxidize any of those metals that we processed. And then after reduction, the metal phase can be separated from our slag phase, and the slag phase can then be used in the construction sector, assuming we've removed all of the valuable metals from it. And then our metal phase will go through a refining process to obtain pig iron and critical metals, and then that pig iron can be used in the steel making process. So here are just a few examples of some of the work that one of our students, Emma Carvo, has done so far, just some visual experiments. So by varying key parameters such as temperature, syngas composition, and gas flow rate, we can see these different visual changes in our final products. We're still obviously working on nailing down our process so we can consistently produce these nice iron beads that we can easily separate from our slag. So some product applications for this process. The final slag can be used in a variety of applications without the loss of metal, such as the construction sector. The recovered iron can be used in steel making. The critical minerals can be used in many different fields for different applications, including rechargeable batteries, superalloys, and cathodes. And yeah, that is all I have for you. I will now pass it over to Jerry to discuss our second process.
Well, thank you, Tegan, and good morning, everyone. Pleasure to be here again. Actually, this is a sequel. About 2 years ago, when we first were funded for this project, a group of us from Montana Tech came to explain what our hopes, claims, and aspirations for this particular project are. And so I'm going to give you an update. As Tegan mentioned, a lot of the work that we're doing now is cutting edge. We're hoping to get a good IP and patent position on it. So forgive us if it might not be as technically satisfying as you might hope, but I'll do my best to convey what's going on. Okay, I'm compelled to inform you that the research that I'm going to be speaking of was sponsored by the Combat Capabilities Development Command Army Research Laboratory, or ARL, and it's been accomplished under a cooperative research agreement with ARL. We've actually got two very large CRADAs at Montana Tech that we're operating under. This one, as I indicated, we're just finishing now our second year and entering our third of the 5-year agreement. This is the overall process flow sheet. I wouldn't hold you to it, but 2 years ago I mentioned, and I gave you 5 black boxes and told you what we had come up with as a predominantly pyrometallurgical method for treating not only rare earth ores or concentrates, but also secondary materials, metallurgical wastes. Practically anything that has an appreciable rare earth element content can find a home in this process. And the way it's constructed, it might not all enter at the front end there where we're showing feed material going in. That would maybe be for primary materials such as ores and concentrates, but they could find other entrance points along the way. So a couple of things. One is much of our work to this point has been done with surrogate materials. However, what I'll be talking about today has been exclusively performed with actual rare earth element concentrates from Wyoming, okay? The other aspect of this, before I leave this slide, I can tell you considerably more about the first 2 steps in the process, and that would be the chlorination roast and the hydrometallurgical leaching operation that leads to the formation of a rare earth oxide precipitate. That then goes on to 3 more pyrometallurgical steps, and these are the ones that are going to be intentionally vague in the presentation. And so what we intend to do there, first of all, our 4 main gangue constituents, our waste constituents, are going to be different compounds of iron, silicon, aluminum, and calcium. Now, as luck would have it, or good fortune would have it, most of those are going to be rejected in that initial leaching step as gangue. However, we're going to have an appreciable iron content that's going to follow through, plus some residual materials that actually do make it into solution and are co-precipitated with the rare earth oxides. So when you see the residual gangue down on the bottom right, that's where we plan to reject that material as one of the pyrometallurgical steps. Following that, there's as you can imagine, in any kind of a mineral concentrate, there's going to be a host of minor elements and different concentrations. So that's the next step in the pyromet process, is to remove those impurities. Then once we have a mixture of purified rare earth elements, those are going to go on to the separation. Okay, this is a key to this process, and this is something that Tegan's work is focusing on right now. We know that the opening steps, we've got those nailed down pretty thoroughly. We'll show you that in a moment. The separation is something that industrially they struggle with. The chemical and physical properties of rare earth elements, as you may know, are remarkably similar, and it's usually differences in the chemical and physical properties that we exploit as extractive metallurgists to make those separations. However, we think we're onto something, and so this is what we're going to be pursuing in the next year or so. Hopefully next year we'll be back here basking in the warm afterglow of some successful experiments and be able to tell you exactly how well they worked. Other than that, we might go into hiding and just never be seen or heard from again. Okay, so the chlorination and leaching, I've got a couple of slides on that. And essentially what we're doing is we're blending our rare earth ore or concentrate. It almost works equally well. We can do whole ore roasting. The problem is it's not as economically attractive to treat a lot of ore than a little bit of concentrate. So we blend that then with a reagent, ammonium chloride, a substantial excess of ammonium chloride, which is in the reaction down below there, the NH4Cl. Put that in a reactor, add some heat, rotate the reactor to get good solid-to-solid contact. And what happens is we're going to produce the rare earth chlorides. We'll have some gangue constituents present. And then, of course, we're going to have an OS gas that's going to contain appreciable quantities of ammonia because of the excess ammonia that we add. And also ammonia is not consumed in the reaction itself. It's just released as a byproduct. Some hydrochloric acid gas, H2O, and then also some carbon monoxide is shown in the reaction below. So the key part is the rare earth element chlorides. What's neat about those is they're highly soluble in just plain old water. Okay, so we can do a simple water leach, get very high extraction efficiencies by doing that, meaning that a high percentage of the rare earth chlorides are going to enter solution. Hopefully we can minimize the amount of gangue and other constituents That's something we're analyzing right now. We do know that we're going to have an iron issue, and that's going to be something we'll deal with downstream. Okay, so here's a couple of photographs. The photograph at left, the rotary calciner, is a thermocraft batch calciner. And so this is what we've been doing to elevate the temperature to about 300, 330 degrees Celsius to get the chemical reaction that we desire to take place. And then actually these two units are close coupled. The two windows, these are the same window, so they're close coupled when we're in operation. So this is where the off-gas reports. This is an absorption tower. We do a lot of adsorption work too, so that's why I'm kind of tongue-tied on that. But this is an absorption tower, so we're just recirculating a stream of water from the reservoir down below up to the top. It percolates down through this packing, and it effectively captures the ammonia and the chloride. So what we can do is take the ammonium chloride, we'll crystallize it, and then return it, because we have to use an excess of ammonium chloride. So this is an economic measure more than anything else. Okay, this slide indicates some representative leach extraction efficiencies, and these would be obtained from the actual concentrate after it had been chlorination roasted and leached. So this is a key, and you'll see it's almost a little bit of a scatter shot, and I'll explain that briefly. But the thing to take away from all of this, you see the lowest point on this might be around 50%. Well, about 50% is the best they do in current hydrometallurgical operations. So this indicates that if everything else downstream of the roasting and leaching fails, we've at least come up with a way to recover more rare earth elements. One other thing I'll point out, if we're dealing with a concentrate, it's difficult, as some of you may appreciate, to effectively concentrate rare earth elements. So maybe you're going to get a 50% recovery through a physical concentration method. If that goes to conventional hydrometallurgy, you might recover 50% more of the rare earth elements. So the mathematicians in the crowd will understand that means we're wasting 75% of the rare earth elements that have been mined. So that's one of the things that we're trying to get away from here. Now, last couple of points on this. If you look at the cerium in the first element there, that's the highest concentration in this particular sample. It's present at about 10% in the sample we've got. So that's really the most representative of the extraction efficiencies. Some of these other elements are present at well under 1%. So you can appreciate if you've got a residual of maybe 0.04, 0.02%, you're going to show a little bit lower extraction efficiency than you had a higher concentrate grade. So that's the reason for the variability in the extraction efficiencies. Okay, so moving forward, our goals, the purification of the rare earth elements. So that, again, is removal of the residual gangue minerals and also taking care of any metals that may have chlorinated during the roast, and iron is the case in point, but there will also be some other minor elements that we'll have to solve. Separation of the individual rare earth elements. As I said, if we do that, we're in really great shape with this process. If we can show that we can effectively separate rare earth elements, we believe we can. Some of the outcomes already realized: higher extraction efficiencies and metal recoveries in the roasting and leaching step. We can dramatically reduce the number of processing steps necessary in order to recover and separate the rare earth elements. And again, I've already talked a little bit about the production of the purified REEs. So looking forward, we've been working with surrogates and a source sample. We're looking for alternatives to feedstock. We want to be sure that this works on a variety of mineral concentrates. We want to look at scrap, anything else that has an appreciable rare earth content that we can bring back into the process. And we'll also look at maybe some other critical metals that might be effectively recovered through a similar process. Scaling, I may have mentioned it. We're planning to convert that thermocraft rotary calciner into a thermocraft auger reactor. That'll enable us to operate on a continuous basis. So we're going to go from gram quantities to kilogram quantities of product, showing that it can be effectively scaled, and also determine the optimal ranges for the various process parameters. You want a very robust process. So if there's operational upsets, you can recover quickly without loss of efficiency. We're also external partners, samples. That's I guess what my plea is. If you know of anyone who has access to rare earth element bearing materials, please put them in contact with us. We'd love to get some samples and see how our technology responds to it. And then last but not least, the implementation of that technology. Lastly, I'd like to have some acknowledgments. Some key members of my research group: Dr. Grant Wallace, a research associate, Katie Schumacher is a postgraduate research associate working with us, and Emma Carvo and Caden Ingraham are graduate students in our group. Okay, thank you, and we're prepared to take your questions.
Great, thank you guys. Questions for Jerry and Tegan?
Thank you. Sorry, I have a regulator question for you. With your off gases, with the combustion of the plastics, or with your process for rare earth metals, are you measuring for dioxin furans and the potential of that?
Well, it's a great question, and it's certainly a relevant question. Yeah, I'm well aware of the potential for dioxin and furan formation. In a past life, before I became an academician, I worked in industry, and I think the first 50 or 60 projects that I ran after I got my PhD were burning dirt, basically to take dioxins and furans, or their precursor materials, out. And so we're aware that if you get these gases, particularly from the plastics, into the gas phase, the thermodynamics take over as the gases cool. So if we don't properly deal with the off gases, you have a high potential for forming both dioxin and furan. So we're cognizant of that, but we just haven't reached a point yet in our research where we feel it's necessary to be measuring them. But thanks for the question.
Okay, more questions? All right, well, thank you, Jerry and Tegan.